So in the last video, we introduced the idea of having a heap style data structure, which meant that top-down rule. So now that we have that, maybe we can think about, how do we actually, implement this, right? What would we maybe think about? Now, one thing is that when people see this, this tree structure that has, nodes linked to other nodes, a lot of times what they start thinking of is, oh, hey, maybe what we should do is have some sort of a linked structure, right? Maybe something looks like a linked list where I have, pointers to left and right child. Yeah, and I mean, you could do that, right? Okay, you can do that. It's fine, okay, we can do better, right? If you ever see me hesitating there, it's because we can do better, right? That's what we always want to do. We want to do better, better, better. So, what else can we think about? Now here, this is actually going to be a little bit of magic here. So what we're going to say is the following. We're going to actually store the data for our priority queue, right? We want it to be structured as a heap in an array, right? So there's no linked structures, it's just going to be an array. So somehow the heap is going to kind of vanish into the background. So let's take a look here at this example. So here we have, right, is we have this heap here, right, that's drawn out for us already. It's drawn out even as a kind of a balanced, complete structure here. Has a bunch of nodes in there. It's all good to go. And then what we want to say is, hey, we're going to store this actually in an array. And so let's look at this for a second. The root node element over here is t. So notice somehow it ends up being over here. Then it has two children, s and r. Those children end up being over here, right? The index is 2 and 3. Somehow, right, the idea is the following. I have an array, right? So I have an array, I have a tree. This first part of my tree, right, will basically fit into the first part of my array over here, right? Then I have my second part, right? These are all of a sudden, these are different layers, right? So this is like, or I should say levels, right? So this is like, level 0, level 1, level 2, level 3. These are different levels in terms of the tree, right? The different kind of depth from the root, or these different nodes. Well, what I can do is I can think about taking those levels one at a time and basically placing them back to back in an array, right? So over here, what I have basically my t, right? So this is my layer 0, if you would, right? Then I have my layer 1, right? My layer 2, my layer 3, right? So I'm basically taking those and placing them one after another, right? And each time they're getting bigger, right? They're doubling in size, right? So initially the size of this first layer, right, was 1. Size of the second one was 2. Size of this one was 4. Size of this one will be 8. You notice it's doubling each time. And it's doubling because each layer could have twice as many nodes as the previous one, right? Because we're working in a binary tree structure, that means that every node can have as most 2 children, right? So if I have to think about, oh, hey, layer 2 has 2 nodes in it, has 4 nodes in it, each of those could have 2 children, that means that the layer after me, layer 3 or level 3, could have, twice as many, could have 8, right? So every time I'll have to double. That means that every kind of segment of my array, right, will have space for any of the children that may exist for the nodes in the previous level, okay? So that's going to be our basic scheme, right? So basically say that we're taking these, level by level and putting them into an array, right? So we can see, right, we have our first level, well, 0th level, first level, second level, and finally third level. Okay, so we're somehow, right, projecting somehow our tree, right, into this heap. Notice that our tree will basically disappear, right? So our program is not going to really handle a tree, right? There's no linked things to connect or unconnect. All it means is we're going to have an array, and this array inside looks like a heap, right? It looks like there's things that go level by level. And so that rule, right, that says top has to be larger than the child, right, that the parent has to be larger, that'll be enforced between different indices in this array, right? So in this case, what we're saying here, right, is that, S, has to be smaller than T, right? R has to be smaller than T. And those are enforced between different indices, right? So let's say over here, right, it's like we have something behind the scenes that says, okay, A, the array, right, of 2 has to be smaller than A of 1, right? That index has to be that size, right? Or this over here, index 3 has to be smaller than A of 1, right? So that's basically saying, is S smaller than T, is R smaller than T, right? That's what these two things are basically giving us. So that rule, right, that says how the heaps should be structured, really that's being projected down into this array, right? So these different slots in the array have this relationship to other slots in the array, right? That's where our tree structure is living. All right, so overall, that's what's going on. Some little bit of background. First of all, we're going to be assuming this tree is complete. Okay, so this is a keyword here, and this is again something you should have seen in a previous class. Basically what it means is that your tree is filled in a certain order, right? So let's say I have a tree, and initially I start with some root node. I should be adding basically in a left to right, top to down order. So here I start with top right, then I add to the left, add to the right. If I add more, I go to left, right, left, right, right. And so I'm going top to bottom, left to right, right? And I always have to fill in a level completely before I move on to a new level. And as I work through a level, right, I always have to go from left to right, right? I can't, jump in between, right? I can't do something like this, right? This is not a complete tree because I didn't go top to bottom, right? I have all these missing spaces here I need to fill in, right? Well, this is the only one that was missing right over here. But I have to go in that order, right? Top to bottom, left to right. That makes me complete. If my nodes have been filled in that order and they're all, filled in, then it's a complete tree, right? So here we're going to assume that it is complete. And later on, maybe I'll have to think about, why is that the case? All right, last thing here, right, is kind of these formulas over here. So these formulas are basically navigation formulas. So let's say I'm looking at, for example, let's say I'm looking at the S in the tree, right? S is at index 2. I kind of wiped out there with my mark, but it's index 2. Let's say I want to go look for its children. How can I find its children? Well, what I would do is basically plug in those values, those indices, right, to these formulas. So I have number 2, and let's say I want to look for the first child, right? S is at 2, so 2 times 2 gives me 4, so that's first child. And then, let's see, 2 times 2 plus 1 gives me 5. So basically what it's saying is my children of, the thing that's at index 2, which is S, right? That should be basically the things that are at index 4 and index 5, right? Index 4, index 5, those are this over here, right? P and N, right? Which is P and N over here. So yeah, these little formulas let us navigate, right? So given the index of a node, I can jump forward to find out what are its children. I can also do the opposite, right? So if I have something like index 6, and I want to know what is the parent of it, I can plug in this other formula over here, this top one, the parent formula, 6 divided by 2, and the floor of that gives me 3, right? So my parent is 3, right? It ends up being over here R. So yeah, I can use these formulas basically to jump upwards or downwards in this tree structure that's being stored in memory. So there we have it, right? That's how we can map our heap structure, right, into array and easily navigate between the different levels, between the different nodes.